Hello everybody, and today we're going to be going over the Galois group of polynomials. My name's Alberto Whitlatch, and thanks for watching this video. Okay, so the goal for the lesson is that students are going to be able to accurately define Galois groups of a polynomial. I also want you guys to be able to correctly determine the Galois group of a polynomial degree less than 5. So let's just get right into that definition of a Galois group of a polynomial. So let P of x be an irreducible polynomial over K. Keyword is irreducible here. We call the Galois group of P of x over K the group of automorphisms of the splitting field of P of x over K. So more formally, what we're saying is this here, okay? So let's jump into some of the basic facts that you're going to have with a Galois group. So let P of x be an irreducible polynomial of degree n over a number field K. Again, I really want to emphasize irreducible polynomial is an important part. So then every automorphism of a Galois group over K of P of x induces a permutation of the set of roots of P of x. Now, also, what we would have is the Galois group is isomorphic to the subgroup of the symmetric group of n elements, Sn. Okay. And last thing is that the order of the Galois group is equal to the degree of the extension field P of x over the rational numbers. So let's jump in right into one of the theorems. So first, we're going to let P of x be an irreducible polynomial of degree 2 over K. Again, I underlined irreducible. That is an important part. Then, the Galois group of P of x would be isomorphic to Z2. So the integers mod 2. So for example, let's say that we wanted to determine what the Galois group over the rational numbers of x squared, the quantity x squared minus 4x plus 2 is. Okay, so now using this theorem that we read up here, if it's of degree 2 over k, so in this case, degree 2 over the rational numbers, since it is an irreducible over the rational numbers, then what we're going to have is the Galois group is going to be isomorphic to the integers mod 2, okay? Now let's just jump right into the next theorem that I want to talk about. So 6.1.12. So let P of x be of a degree 3 polynomial irreducible over the rational numbers, and let x cubed plus P of x plus q be its reduction to a depressed cubic. Okay, so then what we have is that the degree of the Galois group of P of x is isomorphic to the symmetric, the group of symmetric numbers of 3 elements if, so S3, if and only if the number negative 4p cubed minus 27q squared is not a perfect square in the rational numbers. Otherwise, it will be isomorphic to the alternating A3. It'd be isomorphic to A3. Let's go ahead and apply this right to one of the groups, right to an example. So let's determine the Galois group for x cubed minus 4x plus 1. So what we know already is that this is irreducible over the rational numbers. So then by the theorem that we just went through, that means that P of x is isomorphic to S3 if and only if the number negative 4p cubed minus 27q squared is not a perfect square in the rational numbers. So what we can determine here is that P is equal to -4, and Q is equal to 1. So, doing some basic math here, we would find out that -4p cubed minus 27q squared is equal to -283. Since -283 is not a perfect square in the rational numbers, so by the theorem that we just covered just a little bit ago, we would have that the Galois group of x cubed minus 4x plus 1 is isomorphic to S3. Now, I do have another theorem I want to go through. So this is for if when we have a polynomial of degree 4, which is irreducible over the rational numbers. Then the only possibilities for the Galois group of P of x are the following. The entire group of permutations of 4 elements of S4, the order of this group would be 24. The alternating group, A4, the order of this group would be 12. The dihedral group, D4. The group Z4, or the Klein 4 group, K. So, thank you guys for watching. I know that this is a short overview of the topic that we were covering. And again, I hope everybody is safe at home and having a good time. Thanks again for watching.